So a whistle-stop tour through one of the most commonly asked for bits of content in revision, and this is the formation but also the reabsorption of tissue fluid. Now, in this situation, one of the most common diagrams that one would see within a textbook, or perhaps even within an exam question, is a diagram awfully similar to this here. Now, what I've just drawn are the outermost layers of the capillary, the squamous epithelial cells that will make up the tube, the structure of the capillary itself. Now remember that squamous epithelial cells are really thin cells, and when they're butted together, there are going to be perforations between them. And these perforations mean that our capillary is actually slightly leaky, for want of a better word. Now, we've got two ends of our capillary. We've got our arterial end here, and at the other end have our venial end up on the side here. Now, when you start talking about arterial and venous, one of the things that's got to be on the tip of your tongue is you start thinking about pressure. So, where is there a high pressure and a low pressure? Well, the pressure that we're talking about, the physical oomph, the physical pressure that we want to be referencing in this situation, is called hydrostatic pressure. So one might say that actually at the arterial end we have a high hydrostatic pressure, and at the venial end we have a relatively low hydrostatic pressure. Just further down the line. Now, obviously in this diagram, it seems that you've got this end and this end, they're right up next door to each other. There is this indeterminate distance between the two parts, which I'll go through and discuss in just a second afterwards. Now, this high hydrostatic pressure means that small molecules, excuse me, like water, will be forced out of our capillary where we're under this high hydrostatic pressure. What will also be coming out at this particular point will be small molecules, the small solutes that will also be making up the blood plasma itself. Big stuff. So if you think about your huge red blood cells, erythrocytes, will be remaining inside your your capillary, but will also, things that will remain inside there will be huge big macromolecules of our large plasma proteins, far too big to be squished out of these small perforations at this time. So what we have here is all this water and small solids being forced out that will then be bathing the cells around this capillary that we've got here. Awfully handy for the cells, because obviously they need the solutes, the water, for their chemical processes, respiration, protein synthesis, for example. So some of these are going to be will be coming out, bathing the cells, forming tissue fluid around each and every one of these cells. Some of this stuff will be diffusing into the cells, will be used, but a lot of it will just be hanging around within this area. There's a lot of water, huge amounts of water, and we need this water. It can't just keep on coming out of the capillaries. It's got to go back in again. Now, if I take you back to these chaps here, the large plasma proteins, with all this water coming out and with these big solutes being left in, this means that what happens to our water potential in this particular area, our water potential will become more negative, will go down. With all the water and the solutes on the outside here and the tissue fluid, well, this means that our water potential is relatively high and closer to zero. Well, surely then, would one not expect water to be moving from a less negative water potential back into a more negative water potential? So you'd expect water to just be moving by osmosis back into here. What you've got to remember is that there is this physical barrier, this physical oomph pushing in this particular direction. So one might say that our hydrostatic pressure is greater than our oncotic pressure. Oncotic pressure, osmotic pressure, some of that vocabulary you would have had in previous topics that we would have gone through and covered. So at this situation, at the arterial end, we've got water being forced out, we've got our high hydrostatic pressure, and we're creating this tissue fluid. But what's stopping this tissue fluid from just going straight back in again is the fact that the high hydrostatic pressure is higher than the oncotic pressure, than this osmotic pressure that we have, that would ordinarily see water be reabsorbed back into the capillary. So then if I take you down to the venule end that we have down here, and as I've said earlier on, we've got a lower hydrostatic pressure. In fact, our hydrostatic pressure is now lower than our osmotic pressure. So what we have in this at the venule end of our capillary, we have water here outside, and of course there's some water inside the plasma here, but we have a higher water potential here, less negative one, a more negative one inside the capillary itself. So water will just move back into the capillary by osmosis. The water, the tissue fluid, is being reabsorbed, but only because this osmotic pressure, this concentration gradient that we've got, creates a physical bigger pressure than the hydrostatic pressure that we have at this venule end. Now, one of the misconceptions I do want to take you through is that students often expect this to be happening within the same capillary, and that's not the case. If you think of a tissue, you'll have an arteriole coming in very often, then you have this absolute capillary nest, this network, and then a venule will then come out of this capillary network that we've got here. So it's not just going to be the same. It's not going to be the same length of capillary that we're referencing to. Our arterial end of our capillary could be here. You could have another, relatively close bit. It could be over here. But the venule end, with this twisting and turning that we've got, this within the capillary network, is that you might have a venule end of another capillary here, right next door. Now, they're in relatively close proximity to each other. So what's being forced out at the arterial end of one capillary will then be reabsorbed at the venule end of another one that is in relatively close proximity to it. So that's tissue fluid formation, high hydrostatic pressure. How are you actually going to make some notes on this? Well, like a lot of the content that we have, a lot of the topics that we've got, you need to focus on a chronology. Break this down into a step of keywords. That can then be the strong foundation of your notes, flashcards, of revision that you've got. If you can just remember what those keywords are, and then later on, if you can go through and put those keywords into order, and then once they're into order, you can go through and make links between them, then you're showing great understanding of the formation of tissue fluid and the reabsorption of tissue fluid, whilst being able to go through and quote all of these keywords that we've got. Clear as mud, I hope, but I'll leave that with you, and we'll go through and help you out, I'm sure. Take care, bye-bye.